Previous videos we discussed about random variables. In this video we study the basics of random processes. What is random process? Before knowing random process, we just recollect what is random variable. We already seen, suppose if this is a sample space where the dots are showing the outcomes, and if they are mapped onto a real line with some real number, then the function that maps the outcome with the real number is known as random variable, denoted as RVs. So here now we'll go for random process. A random process is a function that gives us the mapping between the sample space to the signals. The signals are nothing but time functions. Therefore, this is the main difference between a random variable and a random process. Random variable is a function which maps the outcome or sample space with the set of real numbers, whereas random process is a function that carries out the mapping between the sample space and set of time signals. The random process is also known as stochastic process. So we have seen that the random process is a function that maps the sample space with time functions. Suppose we have a sample space like this, and where the dots are the outcomes, and they are attached to the signal function or time function, time signals, various signals like this. So each outcome is mapped onto a signal like this. So now it's a mapping between the sample space with the time functions. So alternately, random process can be defined as the ensemble of time function. Ensemble of time functions means, ensemble means group of time functions, is some probability attached to the occurrence of each sample function. Now why they are useful to us? Random processors are very much used to model the noise and information sources, which are essential to the understanding of digital communication. We take one example of random process. Suppose this is a sample space with different outcomes, and each outcome is mapped to a sinusoidal oscillator. Let us imagine that each outcome is a harmonic oscillator. So definitely we have different type of waveforms here. So each harmonic generator is generating a waveform like this, a time signal. And now each one is given as a sine pi t plus theta. Now this random process is denoted as x, t, w. T indicates time, w indicates outcome. Normally the random process is denoted as x, t, w, two parameters are there. T indicates time and w indicates the outcome. So here, if each outcome is generating, in this case outcome is taken as an harmonic oscillator. Each harmonic oscillator is generating a waveform like this, which is a time signal. Then if that waveform is given by a sine pi t plus theta, now the amplitude, phase and the angle of the waveform are random variables. Those are depending on the outcome. Therefore, we have to distinguish the difference between the process and the variable. So the random process maps the sample space with the time function. The random process is the ensemble of the time functions. But for a given outcome, the generating a waveform. For example, in this case, this is a harmonic generator, which is generating a waveform within equation A sin pi t plus theta. Here in this case, amplitude and phi and theta are the random variables. They are in fact real numbers. So they are known as random variables because that for a particular outcome they are generating a fix A, pi and theta. Now if I write xt1w, it means the random process at the value of t1. How it looks like? Suppose if I am taking any time incident t1, I am marking with red. It is at t1. Suppose if I am marking it at t1, at time t1, if this is the marking, then it has got some value here, it has got some value here, it has got some value here. So at time t1, at a specific time instant, all sample functions are yielding certain values. All of them are random variables. So now we need to distinguish between various notations. X, T, W denotes the random process where T is time, W is outcome. We can normally ignore the outcome and we may simply write xt to denote random process. Now if I write xt1, it is the value of process at time t1, which is nothing but a random variable as I marked it in this diagram. So capital X within the brackets t indicates random process. Capital X within the brackets t1 indicates the value of process at time t1, which is a random variable at time t1. If I simply write small xt, it is a time function. So this is the distinction between various terms like random process, random variable and a simple function. So as I said, a simple notation for random process is xt. Now we will recollect for a simple random variable what is the notation? The notation is capital X. For random process, the notation is capital XT. We discuss joint cumulative distribution function and probability density function of random process. Before that, we just recollect the joint CDF of multiple random variables. Suppose if we have two random variables x and y, we are writing the joint CDF for multiple random variable as fxy within brackets small xy is equal to probability of x less than or equal to x and y less than or equal to y. This is how we are defining joint cumulative distribution function for two random variables xy. Now we come back to random process. In the random process, depending upon the time epochs, we have different random variables. Suppose at time t1, we have the random variable xt1. We will consider the random process xt. So at time t1, we have random variable xt1. At second time epoch, at t2, we have random variable xt2 and so on. In general, suppose if we have L time incidents, at L time epochs, we have xt1, xt2, dash dash xt1. All these are random variables. So in general, the joint CDF, the capital F xt1, xt2, xtl within brackets x1, x2, xl is given as probability of xt1 less than or equal to x1, xt2 less than or equal to x2, dash dash xtl less than or equal to xl. It is similar to that of the joint CDF of multiple random variables. In the case of random process, depending upon number of time instants, we have so many random variables. Therefore, in general, the joint CDF is given as this. Now, what is probability density function? The joint probability density function, as we have seen in the case of the multiple random variable, that is given as fxy is equal to dou square by dou x dou y fxy xy. So it is double the differentiation of the cumulative distribution function. The same principle can be adopted in the case of a random process also. So if we want to have joint probability density function, that is given as the partial differentiation of joint cumulative distribution function. So as we have L random variables, L times we have to differentiate it partially, the cumulative distribution function, then you get joint probability density function. Now we define IID random process. What is IID random process? It is known as independent and identically distributed random process. What does it mean? If all random variables have got similar probability distribution and all of them are mutually independent, then those random processes are known as IID, that is independent and identically distributed. To explain this, let us take an example. Suppose we have a basket like this, which has got few red balls, like I shown here, and we got few blue balls, and we have few green balls. Now as an experiment 1, you randomly pick up one ball from this basket. If that happens to be a red ball, keep it aside. Suppose if this happens to be a red ball, keep it aside. It has got some probability. Now as experiment 2, again I conduct and randomly pick up one ball from this. Suppose it happens to be green. Now the outcome of the second experiment depends on the first outcome, because the number of balls in the second case are not same as in the first case. The number of red balls are less. So they are not mutually independent. Suppose if I repeat the same experiment, now I am keeping, after picking up the red ball, I am keeping the red ball again back here and conduct the second experiment. In this case, the probability distribution is similar for all experiments. So this is known as IID, independent and identically distributed random process. The good example for IID random process is MATLAB generator. While doing MATLAB experiments, if you go for random number generation, whenever you are generating a random number, it generates a sample function of IID random process. So these IID random processes are used in modeling and simulation techniques. We can write random process in terms of orthogonal functions. Suppose we have time signals, finite energy signals, we can write them as the sum of the product terms of coefficients and orthogonal functions. Like in Fourier series, we can represent any finite energy signal in terms of its coefficients and orthogonal functions. Similarly, we can represent random process in terms of the coefficients and orthogonal functions. So it is given as Zt is equal to sigma for all values of k, Zk into pi kt, whereas the pi kt is representing the orthogonal functions and Zk are representing the coefficients, and they are all random variables. So any random process Zt can be represented in terms of the random variables and the orthogonal functions. This concept gives us a framework to model physical noise sources. So in this video, we discussed the basics of random process. We have seen the difference between random process and random variable, and we defined joint cumulative distribution function and probability density function for random processes, and we understood what is independent and identically distributed random process, and we have seen how to write a random process in terms of its coefficients and orthogonal functions.